Thanks, Alan. Right, so I will give the third talk of the series. The first two are given by Jin. And in this talk, I will talk about these this dichotomy theorem for planar instances. Here's a rough outline of what I'm going to talk about. So I firstly review some of the notions and notations that has already been covered by Jin. And then I will move on to some tractable cases. This is also mostly covered by Jin already. And then in the end, I will discuss some hardness proofs. And in particular, I will showcase a particular lemma that is quite useful in our dichotomy theorem. And it's kind of nicely shows some techniques that we use very often. Okay, let's start. So first of all, we have our favorite problem, the counting, the CSP, constraint satisfaction problems, and we are interested in the counting version. So again, we have a set of variables and we have a set of constraints, and we connect them if a variable is in a constraint. And equivalent, we can view this as a hypergraph or equivalent like a bibottized graph. So formally, we have this definition. We have a bibottized graph, and we sort of label the constraint set by a function from a certain function set f. And we want to compute this partition function, which is sum of product quantity. And it is sum over all possible assignments of the variables. And the weight of each particular configuration is just a product over all functions. Okay, and here we are mostly interested in the complexity in terms of these function set f. So we know like a set is hard. We know like easing in planar graphs is easy. So our question is like when is it hard and when it is easy. So that's the classification program. Okay. And one of the central problem in counting complexity is to count the number of perfect matchings in a graph. This is one of the first number p hard problem introduced by Valent. So here is just a brief reminder of what a perfect matching is. And our goal is to count the number of such structures, such perfect matchings in a graph. And somehow counting perfect matching is not really a CSP because, for example, we have this paper by Friedman, Lofars, and Shriver. It can be probably shown that counting perfect matching is not expressible in some so-called vertex assignment models, which is very similar to graph homomorphism and spin systems. So it's somewhat difficult to express exactly in CSP. But we do have actually a CSP that is equivalent in the approximation sense to counting perfect matching, which is Ising model with some negative weights. But here we are mainly considering the exact computation. Okay, so that urges us to consider sort of an edge coloring model. So we want edges to be variables because we want to pick a perfect match. We want to pick a subset of edges, and the vertices are functions. Okay, so this gives our motivation of so-called Holland problems. This is because this sum. This quantity first is denoted by Valent. He called this Holland. So the instance is given a graph, and we have these edges as variables, and we label each vertex by a certain function, from a set of functions, and we want to compute this sum of product quantity. You may already notice this is sort of a special CSP problem where every variable appeared exactly twice. So sometimes this is also called like read twice CSP. But that's like a restriction on the instance side. But we are interested in sort of the complexity with respect to the function set. So in that point of view, this is actually more general than counting CSP. Because we can simulate a counting CSP by easily throwing in all the equality functions. Since if we have a variable that appears, say, d times, then we can just replace it by a equality function of arity d. This actually goes both ways. So if we have a dichotomy theorem for all function set for Holland, then as a consequence, we have a dichotomy for counting CSP. So in this sense, it's slightly more general. And this is actually has been studied before. There are some equivalent formulations such as like reductive CSP or maybe graphical CSP, and also this is equivalent to tensor network contraction. This is how these things sort of connected to quantum computation, because quantum circuit can be viewed as tensor network. And here is the notation PL Holland. It just means every input graph is planar. And so let's see a brief example with how we can express counting perfect matching as a Holland. So what we do is just we put this exact one function on every vertex, and note that we put actually different functions when the degree is different, like exact one of arity 3 or exact one of arity 4, when the degree is at 3 or 4. And then the counting perfect matching is just this z, the partition function. Okay, and as I said earlier, counting perfect matching is one of the first number P hard problem given by Valent when he defined this class. But like roughly attacked earlier, it's already known there's a polynomial time algorithm to count perfect matchings in planar graphs, and this is the so-called FKT algorithm, or like Castellan's algorithm. It's via affine orientations of planar graphs. This is what Jin talked about in the first talk. And also, Valent have this wonderful idea of holographic algorithms that kind of extend the reach of FKT algorithms. So as we understand now, like this roughly have two ingredients. First, we have these match gates. So roughly speaking, these are the functions that can be expressed by perfect matchings sort of via a planar gadget, as in the Andreas talked about the gadget sense. We restrict to planar because we want to solve the problem in the end by this FKT algorithm, which only works for planar. And the second ingredient is that these holographic transformations, which is roughly a change of basis. Okay, let's briefly review what a holographic transformation is. So we use this notation Holland FG to denote the case where the input is actually a bipeptide graph, and on the one side is F, and on the other side we get G. We need to consider bipeptide graphs because when we want to apply transformation, we will apply T on one side and T inverse on the other side. And this is actually quite useful because we can always write a Holland as equality 2 on the edge side by considering sort of the edge vertex incident graph. Okay. So this is the transformation, and here let's see another example of what holographic algorithm can do. I will talk about the easing model. Last time, Jin talked about something called planar 3 regular not all equal ice model. That is sort of something new that when Valent introduced it. When Valent introduced holographic algorithms, this is a new problem that can be solved. But there exists this easing model are sort of more classical and already known to be solvable. We can view it in terms of these holographic algorithms. So the easing model just gives some edge interaction beta 1 and beta, and we sort of give assignment to every vertex, like 0, 1, or blue or red, or like plus minus, spins or states or whatever. We have these interactions. If they are equal, give beta. If it's disequal, give 1. And for each configuration, we have this weight, which is multiply all edges. And the probability of a particular sigma is like proportional to the weight. And we are interested in calculating this partition function, which is sum over all possible such configurations. Okay. And planar easing without field is a tractable problem. And to show that, we first we recall some notation. This bracket notation is for symmetric function. We just list its entries by Hamming weights. So Fi is like the entry, the function value when the input has Hamming weight I. And using this notation, we will write like equalities like 1, 0, 0, 0, and 1. It is 1 if and only if all inputs are 0 or all inputs are 1. And like the perfect matching function, the exact 1 function is 0, 1, 0, 0, 0. That is, it is 1 exactly when one of the inputs is 1. And the easing function is like beta 1, beta. It's a binary function because it's put on every edge. And again, as I explained earlier, the easing is like a sort of a CSP. And we can view every vertex as an equality D function. And so if you know that if there's an external field, then we will have a generalized equality. But here we consider no field case, so we have an unweighted equality. And then we can write easing in this way. So we have a sort of equalities on one side, and we have this beta 1, beta on the other side. Then we will do this transformation H, which is the Alamard matrix. And this H is itself the inverse. So when we do the transformation, we will do H on both sides. And on the vertex side, we rewrite this equality in sort of a tensor form, which is 1, 0 to the tensor D, or plus 0, 1 to the tensor D. So again, it's the same vector, it's the same 2 to the D length vector, which is 1 if it's all 0 or 1. And we can distribute it and compute this. And here I ignored some constant factor because it doesn't affect the complexity. So we get this expression, which is basically a parity function. It is 1 if and only if the weight is even. Excuse me. And on the other side, on the edge side, we do the same sort of thing. But notice that here we view the vectors as row vectors. Here we, on the other side, we view it as a column vector because it's sort of a huge dot product. And we do the transformation, we get something like beta plus 1, comma 0, comma beta minus 1. And Jing last time gave a explicit table of what are symmetric match gates, and both of them are match gates. So we can express these as perfect matchings and then solve it, use FKT algorithm. So this sort of transformation is also the so-called high temperature expansion, or something called the subgraph word, because edge functions are transformed into a sort of a weighted equality. So if you look at this view beta plus 1 over beta minus 1 as a weight, then it's just a weighted equality. So it's like picking a subset of edges, and essentially the Jerome Sinclair F pitas for ferromagnetic easing is under this view as well. And we can even generalize this to sort of a domain size Q by replacing the transformation by discrete Fourier transformation. We will get some mod Q gate here and some kind of equality here, but that doesn't seem to give us any useful algorithm though. But in the Boolean case, it's quite handy. It gives us the planar tractable algorithm and it gives us the F pitas. Okay. All right. So we have these holographic algorithms, and when Valent introduced them, he called it somewhat accidental algorithms. So we want to understand what are their real power, like what can they compute, what can they not compute. And Jin and his collaborators has done some extensive work to understand the power of what holographic algorithm can solve. But the question still is not that satisfying, because we still wonder, like, what about those that it can't solve? And that motivates our classification program. So as we noticed in sort of previous works, these counting problems, they are defined by local constraints, and they usually can be classified into 3 classes. So the first is those that are tractable. These are polynomial time even in general graphs. Second kind is like they are hard in general graphs but solvable in planar graphs, like counting perfect matchings or like these match gates. And the third kind is like this. It's very, very hard. It's even hard in planar graphs. And as we observed, The second category is usually like always captured by holographic algorithms with the match gates. Here are some examples, such as Todd polynomials and like two-spin systems and Boolean counting CSP. All of these are in exactness again. However, last year we discovered that for planar Holland, it's not quite the same. It's somewhat ironical because Holland is the framework where we should consider perfect matching. But for those that this is not the case, we have one extra case that are planar solvable but hard in general. So again, we have this dichotomy where we have a set of functions which is symmetric and complex weighted and Boolean. And we show that this problem is number hard unless one of the cases will happen. So first case is that it's tractable even in general graphs without a planar restriction. And the second kind is there exists a transformation such that it became a match gate. So that means it's solvable by holographic algorithms. And the third kind is somewhat special kind of counting orientation problems. As Jane said last time, counting orientation is just to put a DC equality function on the edge side, which is equivalent to the normal Holland setting by the 1,1i minus I transformation. Because we are considering complex weights, so that is also in our framework. And the first class is characterized by our previous work like 3 years ago. And the third one is orientation problems are somehow not captured by holographic algorithm. And here we will discuss about it a little bit later. Okay, now let's move on to the tractable cases. I will go through these tractable cases, but Jing has already explained some of them, so I will not give much detail. The first class is these so-called affine functions. So basically, you have a affine support indicated by this character function, and we have I to some quadratic form. Here we require B to be symmetric. Therefore, the cross terms will always have an even coefficient. And this is called affine because it's a generalization of like affine linear systems. We can count the solution to affine linear systems, right? And this is a generalization to that. And interestingly, this also corresponds to something called Clifford gates in quantum computation, which is classical, which can be simulated classically efficiently. Well, the reason is it's tractable. So the word is still some consistent. Okay. And the second type is this product type. It's basically products of equality and disequality. This is very easy to solve because you can just propagate. And so the class is match gates. These are only tractable in planar graphs, which Jane has covered in his previous 2 talks. And lastly, there are these vanishing cases, which will sort of always return 0. I think Jane didn't have the time to talk about it, so I will talk more about this in a few slides. Okay, so what about vanishing? Here's a proof by picture. They vanished. Okay, more seriously. So the first observation is that 1i is vanishing. This is very simple. You do dot product of 2 1i's, you always got 0. And we can do something more complicated. We can suppose we have degenerate signature, a degenerate function, which means it can be decomposed into a bunch of unary ones. And suppose we have more than half of these unary ones are 1i. Then this must be vanishing, because whenever you have this function, only this function in the instance in the sort of tensor network, you can always decompose it, and there will be more than half 1i in the network. Then two of them will definitely match whatever you align them. Then whenever this matches, it gives you a factor of 0, gives the whole, making the whole sum 0. But that's not quite it, because this is not a symmetric function. So we need somewhat to symmetrize it. Here's a definition of some symmetrization operation, which is just sum over all possible permutations of these unary ones. It's very easy to understand once you write down example. So here we symmetrize this 1i 0, 1 thing, and we got these three terms, and we have this factor of 2 because when we swap 1i and 1i, it's the same thing, and we'll get this expression. So after we symmetrize it, we can view it as a superposition of like sort of three functions, three degenerate functions. We either got this one, or got this one, or got that one. When we have an instance of these functions, we will view every vertex as in one of the three states. It gives one of the three functions. And then we can write the whole sum in sort of 3 to the n many terms. This is usually not very useful because it's still an exponential sum, and it doesn't really give us any efficient algorithm. But here it does, because whenever we write this way, we will have more than half 1i's, and in the whole graph, no matter how we put these things, there will always be more than half 1i, and 2 of them will match. Whenever it matches, it gives us 0. Although it's a exponentially large sum, every term is 0. Therefore, the whole sum is still 0. So that's basically the idea of this vanishing stuff. And as Jing said, we can throw in something more so that the whole sum in the end is not necessarily 0. It's actually a little more than this. But this is a rough idea. Okay. And so a few comments on these tractable cases. The first is that this is a gadget, and here is the sort of expression of this gadget. This Andre has discussed about gadgets constructions in detail. And here I want to point out that like this if a tractable class is maximal, then it has to be closed under gadget constructions. And in fact, all of these 4 classes, they all satisfy this. And more importantly, they kind of satisfy a efficient gadget construction. What do I mean by that? So we actually can have a universal approach to all of these 4 tractable cases. So it has sort of two ingredients again. First of all, we have a succinct representation. By succinct, we mean polynomial size in terms of this arity. And this seems to be trivial for symmetric functions because we can just list the sort of d plus 1 many entries. Is definitely polynomial. But in fact, all these 4 cases, we can define them for asymmetric ones. And when it's asymmetric, it has potentially 2 to the n many bits, 2 to the n many information, but there always exists a succinct representation for any of these class. Like for affine, we really only need to store the information of the matrix A and B, each of which is like n by n, so it's like n squared many bits. Product type is easy to do, it's like linear in many ways, many bits. And match gate, this is due to match gate identities. We actually only need n squared many bits, well, big O of n squared many bits to memorize it, to store a match gate. And vanishing as well, it's like linear. Okay, but that's not enough. Many functions has this succinct representation, but this succinct representation can be updated efficiently whenever we do the following 2 basic operations. So we have this operation, which is sort of this is also showed by Jing in last talk for the Fibonacci gates. So basically, we have two functions. We just connect one edge among them, and we view it as a new function. And the second move is that we have a function, and we just do a self loop, and we view it as a new function. So notice that given any graph, we can repeatedly do these 2 moves to construct the graph. So given an instance, we first cut all the edges, then we connect them, and when they are in the same component, to connect them again is like to do a self loop. And we do this until we have only sort of 1 vertex left, while maintaining this succinct representation. And in the end, we will get a nullary function. And nullary just means there's no input. No input means there's only 1 value, which is exactly the whole sum. Okay. in fact, the algorithm for general higher domain CSP described by Xi Chen is somehow also fits in this paradigm. This seems to be a general theme of how these things are tractable. However, this is somewhat arbitrary. Like, there are many things that have succinct representation, and you may imagine that many of them can be updated efficiently. But by our dichotomy theorem, these are the only things. Like, there are actually not many more. Well, there are other cases that I will discuss later. But they are mainly this whole thing. And this is actually not how match gate is solved, you would imagine, because as we pointed out earlier, match gates can be reduced to counting perfect matchings, and counting perfect matchings is like we do ffine orientation of the graph, which is a global thing rather than these local moves. But due to match gate theory, due to the match gate identities, we can verify that these moves will maintain the match gate identity. Therefore, it can be understood in this way. This is sort of an alternative proof for the Castellian algorithm. This is actually due to a new proof by Mingji Xia. Okay. So if we are considering CSP, we should stop here. Like for CSP, this is it. But we are doing Holland, and for Holland, there's one more thing to consider, which is this holographic transformations. So here is the definition of so-called F transformable. Basically, we write the Holland in this bipartite way, and we do a transformation T, and we put these two functions together. The complexity can only increase. And so we call this F transformable if both of these two functions belong to the same set, function set F. Therefore, we can reduce this small f to script f. The point is, if script f is tractable, then any f transformable functions is tractable because it can be reduced to f by these transformations. Okay, then interestingly, this vanishing set is closed under these transformations. Well, it's sort of intuitive because it always gives 0. Like whatever you transform, it always gives 0. But the other three are not. So this is where things differ from CSP, I think. In CSP, you only consider these 3 cases, and we don't need to consider these transformations. And moreover, like the gadget construction is sort of commutative with transformations. So therefore, we only need to consider a gadget closure, then consider a transformation closure, and we don't need to repeat this process to get sort of a maximal tractable case. And these 4 cases are actually the main tractable cases for planar Holland, the A, P, M transformable, and the vanishing case. Another view to understand V's closed down transformation is that sort of 1i, 1 minus I business, they are always the eigenvectors of 2 by 2 orthogonal matrices, because orthogonal matrices will preserve equality. Okay. But notice that I said these are sort of the main tractable cases. There's one more case that we discovered, which is not really, which doesn't really fit in the picture I described earlier. These are some problems about counting orientations. Remember that this is equivalent to normal Holland via this 1,1i minus I transformation. And in these orientation problems, we consider 2 kinds of nodes. The first kind is like exact one function. It's like we allow exactly one edge to come in. And the second kind is like equality functions. We allow all edges coming in or all edges going out. So it's like either a sink or a source. And we have further requirement that the GCD of all these vertices in the type 2 is at least 5. Notice that we requirement is like GCD. So if you have degree 5 and degree 6, then GCD is 1, and the problem is hard. But if you have like 5, 10, 15, the GCD is 5, and the problem is easy somehow. The algorithm is kind of a cascading phenomenon because instance has to be planar, and because this sort of degree rigidity, there will exist some structure such that some of the edges has to be pinned to 0 or 1, or there's no satisfying assignment. So we will argue that either such thing exists, or the instance can be solved by one of the known cases at A, P, or M. So we will repeat this process. We find a structure, we pin an edge, and we find another structure, and simplify the instance furthermore. In the end, it will be a solvable instance by known algorithms. So this is somewhat exotic and kind of artificial problem. But due to our dichotomy theorem, this is the last missing piece. Like once we understand this, everything else is sort of hard, like number P hard. So there's no other weird cases. Okay. It's actually, we stuck at this for quite a while. At first we thought it has to be hard because it's so weird, but somehow in the end it turns out to be easy. Okay. So that's about it about the easy stuff. Let's talk more about the hard proof, or maybe hardness proofs. Okay. So the general strategy of our dichotomy theorem is kind of we prove a dichotomy for a single function first. In general, we want to consider a set of functions, but it's somewhat too complicated. And we do a single function first, and we do an induction on the arity of the function. So induction has like sort of two steps. We consider base case, and we consider an arity reduction procedure. Usually, this reduction is like easier to do by arity 2. So we have two base cases, 3 and 4, and once we have a single dichotomy, then we want to show that different tractable cases cannot mix together. If we mix them, they become hard. However, like this is like the high level outline, but what we really do is more of a convoluted thing. Like we prove some single thing, then we prove some mixed thing, then we use mixing to prove another single thing, and so on. And the real proof is more complicated than that, but this is a high-level idea. And in particular, in this talk, I will show a concrete lemma. And in fact, we will show that most of the arity 4 functions are number P hard. This is one of the base case. Remember, we have base case arity 3 or 4. And this is quite a useful lemma, I will see later. It's quite handy in the proofs. We use it in many places later on. Okay. So suppose we have a arity 4 function. So we consider symmetric functions. So it has sort of 5 entries in the bracket notation: f0, f1, f2, f3, f4, and we write it in this matrix notation, which is we sort of index 2 inputs as so 2 variables as input and 2 variables as output. So it's like 0, 0, 0, 1, 1, 0, 1, 1 to index the row, and similarly for the column. And we write it this way. And in general, for a asymmetric function, we can write down this matrix G of 0, 0, 0, 0, 0, 0, 1, 0, and so on. Notice that usually we label the variables counterclockwise, but in this matrix notation, rows are indexed like x1, x2, and the columns x4, x3. We reverse, we swap the order here. This is easier to understand with a picture. So we list the variables like counterclockwise, and we label it this way so that when we concatenate two such functions, the resulting function has a matrix which is just the product of the two matrices. Here I used a diamond to denote the most significant bit, and here's the most significant bit. So like x4 aligns with x1. That's why we list it this way, and viewed as a new function, we put them here to notice the most significant bit. So this signature matrices notation. And in particular, we are interested in these so-called redundant matrices. What we're really interested in are the symmetric functions, right? And somehow symmetric functions are too restricted in this view. So we slightly relax it. We consider redundant matrices, which means the middle two rows are identical, and the middle two columns are identical as well. And notice if it's symmetric, then f1 equals f1 prime, and f2 prime equals f2, and equals f2 double prime, and so on. So symmetric functions definitely have a redundant matrix, but reverse is not necessarily true. And since it's redundant, we want to compress it. So we have this compression operation, which is just sort of to delete one of the redundant rows, and to delete the redundant column, and we put a 2 in the column. We need to put this 2 because we want to maintain this to be a sort of semi-group isomorphism. We want to preserve the multiplication. So define this in this way so that if MH is like MF1 times MF2, then the compression also has this multiplication. Okay. Now here is the lemma I would like to show here. So let f be a relative function with complex weights, and suppose the matrix notation is redundant, and the compressed matrix is non-singular. Then this problem is hard. Okay, so that means like many of these problems are hard because our only constraint is determinant is not zero when you compress it. Okay. To show this, we have like 3 steps. First of all, we want to show sort of a planar, counting planar 4 regular Eulerian orientations, number p hard. This is what Zheng Yi covered in his last talk, but I think he didn't have the time to explain the motivation. This is the motivation. This is why we consider this problem. We first show this is hard. I will not repeat this part in this talk. Then we will reduce sort of the identity element in this semigroup, in the redundant matrices. We can always reduce from the counting Eulerian orientations in planar for regular graphs to this problem. And lastly, we show that everything else can be reduced from the identity element. So the first part is covered by Zheng Yi, and I will talk about the second and the third part in this talk. That will be the rest of my talk. Okay. So what is the identity element? It corresponds to the I3 in the in GL3 in the 3x3 matrix. So we sort of uncompress it. We get this matrix. I will have 1 in the corners, and we have 2. I will have 4 halves in the middle. Okay. Remember that when we do the compression, we put a 2 in the column, so we get this. Okay. And this identity is hard because we can reduce it from the counting Eulerian orientations. Remember that counting Eulerian orientation can be written as Holland by put like a DC equality on the edge side. Then we do transformation. We actually get an integer value of the problem 3, 0, 1, 0, 3. So our reduction will be from this 3, 0, 1, 0, 3 to identity. Okay. And yeah, this reduction is actually a approximation reduction. So somehow when we use gadgets for approximate counting, it's like to use the exact computation, the exact reduction for approximation problem. Here we do the reverse. Here we do an approximation reduction for exact counting problems. The idea is actually very simple. We can sort of approximate this function exponentially accurately. Because our problems are integer weighted, and well, here we just normalize it so that it's like a rational weighted. The true value will be in sort of granularity, like 3 to the n, 3 to the minus n. So if we can approximate it accurately enough, like in the exponential sense, then we can just recover the true value. So we can recover the exact computation. And here is a recursive construction to how to approximate this. So first we have one node. Then we do a rotation. We put the most significant bit rotated like 90 degrees. And we attach another one. And again, we do the rotation. And we attach another one. We do the rotation. We attach another one. So what this is doing is kind of complicated. But we will show that this operation gives us a very good approximation of that. So we claim that the matrix of this gadget is something like this, where A sub k is like a third minus some exponentially small error, and what we want is like a third for all these 6 entries. So this is a very good approximation. Okay, and what do we really do when we do the rotation? The entries goes in these cycles, and this is just a pictorial illustration. So in this construction, we do a rotation, then these entries go along these cycles, and we attach a new one, which is this half-half thing, and effectively this is just averaging the middle 2 columns. And it's not hard to verify that the average of these two are closer to a third, so it's AK plus 2. So we can realize this, where AK is exponentially accurate, and we want to approximate this. Then we only need to make sure the error is smaller than 3 to the minus n. And so we can recover the exact value. And it's not hard to verify that this works out when you pick, say, k to be 4 times n. Okay, so this is a very simple proof, actually. And so let's back to the lemma. So we have shown the identity is hard. Then what we need to show is to reduce everything else to it. And this proof will be more complicated, and we will do it by the interpolation technique, which is a very common used technique in counting complexity, and is actually very strong. So the basic idea is that, say we have a sort of a matching polynomial, then we will, so we want to write the whole and sum as in some kind of polynomial, such as like a matching polynomial, and we want to solve the coefficient of the polynomial. Like each coefficient ck is like the number of matchings with size k. But here is slightly more complicated than the single variable polynomial, but still we want to do this interpolation. Okay, so what we do is a sequential construction. Remember that we wrote this, we choose our notation in this way so that m of ns is like mf to the s power. And we do this recursive construction. It's just to multiply this one at a time. Okay. And to do the interpolation, suppose that the identity appeared n times in the original instance called omega. Omega is basically the graph G plus the labeling. And we want to replace this identity by the gadget. So by this gadget we obtain here, but we have an index S. So when we repeat this construction s times, we get some instance called, say, omega s, and the matrix is just this to the s power. So when we have this matrix power, we just do the Jordan normal form, and this, in general, it will have something like this, with some eigenvalues lambda 1, lambda 2, lambda 3, and possibly 1 or 0 b1, b2s. Here we will consider a case where all 3 eigenvalues equal and both b1 and b2 are 1. The reason is we will see later on that when we do the interpolation, we get some linear system that is that will be singular in this case. In other cases, you usually get a non-singular linear system, either non-singular linear system or it's finite order, which means you can directly realize identity. Here is a little more tricky. We will get a singular system, but we'll still kind of solve it. Okay. So here is a little trick to do the interpolation. Because we can write this as this t lambda to the s t inverse. But the original one, we can also write it in this way because it's identity. In some sense, this is kind of a discrete holographic transformation, if you think about it. So what we do is we replace each occurrence of this by three matrices, three functions, each of which corresponds to the three matrix T or ID or T inverse. And similarly here. So what we care is the contribution from this lambda and this ID. Okay. So we do some stratification. We will consider assignments to this matrix to the s power according to like 0, 0 or 2, 2 I times, and like 1, 1 j times, and so on. We have like sort of in this picture in this matrix we have 5 non-zero entries, but when we take this power, the corner will also be non-zero. So we have 6 cases, but we bundle the 0, 0 and 2, 2 case together, and any other assignment will give the 0. And in the original instance, because we have identity here, we have 1, 1, 1 here, so we only care about 0, 0, 1, 1, 2, 2s. Okay. Now we can rewrite the Holland sum in terms of these C, I, J, K, L, M's. So this is similar to like the CK in a matching polynomial. In matching polynomial, it is just the number of matchings of size k, but here is some assignment, some contribution when the assignment satisfies the parameters I, J, K, L, M. It's just 5 parameters, but it's the same spirit. It's slightly more complicated. Okay. And we write this Holland sum in this way. Then in the original one, because we only care about I and j, so all others are 0 to get this sum. We have this factor of 2 because when we uncompress it, we get a half in the middle. And for omega s, we get this expression. It's not very hard to work out. And so we have this C, I, J, K, L, M's. And our goal is to solve this by oracle calls to the Holland of omega s. And once we solve them, and we can plug in the Cij 0, 0, 0s in this sum to recover the value of the original instance. But somehow this system is rank deficient. Like we can't solve it. A very simple example here is just like if we have x plus y plus z equals 1 and x plus y plus 2z equals 2, we can't solve x and y. We know z equals 1, but we only can say like x plus 1 equals 0. Our system, if we look at it, we stare at it like 1 minute or so, we will realize that for this term, as long as k plus l is some number and m is another number, then any of these terms will have the same coefficient. It's similar to this, therefore we can not solve them exactly, but we can solve the sum of them. And that's good enough somehow, because xqm, we can define this xqm, which is to let k plus l to be q and m is m, and I plus j will be n minus them. And the original Holland value is just the sum over this I plus j equals n of Cij 0, 0 and such. This is exactly x 0, 0. And so if we can solve this x 0, 0, then we can also recover the original value. Then we get a new linear system looking like this, where s is the index. And okay, let's write this thing as the alpha as a coefficient. Is this? Can we solve this? The answer is still no. Unfortunately, this is still a rank deficient system because it's not hard to observe this identity. That means that there are like this. The column indexed by q and m can be written as the sum of two other columns. So we have this equation like qm is like q minus 1m plus q minus 2m plus 1. So that means we need to do more operations. So what do? We sort of split xqm, distribute it into the two variables q minus 1m and q minus 2m plus 1. And so we will define new variables recursively from q equals n to 2 to do this thing. So the new variable will be the plus, so xq minus 1m will be xqm plus the old xq minus 1m, and similarly for q minus 2m plus 1. So let's see what this operation really does. And we can write down these variables in a triangular way. And for concreteness, let's say n equals 6. We'll start from x60, and we will rewrite 50 as the old 50 plus x60, and 41 as 41 plus 60. And recursively, we'll do this for 50 and 51. And we'll do this for 40, 41, 42, and so on and so forth. Then we do after we're doing all these things, we will get another system, and for which the unknowns, we don't really know what these unknowns mean. Like each of these new variable will have contributions from a path to this x60. However, one thing to notice is that x00 sitting in his lonely corner is untouched. So x0, the only value that we care is not changed after all these operations. And indeed, after doing all these, we can show that the system is of full rank, and we can solve it. That means we can solve x00, and it means we can solve the value of the original instance. Okay, so this is interpolation proof of one of the cases. In other cases, this system, we don't need to do all this stuff. We just show it's full rank. It takes some effort, but it works out. Okay, so let's finish my talk with some remarks. So in proving these dichotomy theorems, the first thing, at least what I do, is to guess the tractable cases, and the next step is just show anything else is hard. Okay. However, each time I do these things, there are always some new tractable cases. When we go from CSP to Holland, we discover these vanishing things. When we go from Holland to planar Holland, we discover this orientation, counting orientation stuff. So the question is, like, is there more? Like, if we extend further our sightings, are there some undiscovered lurking trackable cases? That's what I think is the most interesting question. And to consider some further future directions, we kind of understand the planar graphs very well now. But what about more general H-manner free graphs? I believe we don't even have a good understanding for counting perfect matchings in H-manner free graphs. I think Radu's talk this afternoon will talk more about this direction. And also we can extend to like higher domains. We can extend to asymmetric functions. And again, the question is there more tractable cases? And can we find them? Can we show anything else is hard? Okay, that's it. Questions?
So do you have a explicit conjecture for this closure as a connection with tractability? You can use the dichotomy theorem itself.
Yeah, this is.
You say so far.
Yes, yes.
You always say symmetric functions.
I'm not sure actually, because let's say in planar graphs we have this new orientation problem. I don't really know how to explain that in this closure sort of business. Right? For the other cases, for the other four classes, we have understand it like very well, and we can explain it. We have this nice explanation of this universal approach. But for the new thing, we don't really know. I think that just means we haven't understood everything yet.
For one thing, we don't really have an explicit conjecture. As you say, the first line, yes, the tractable. In the asymmetric case for the planar Holland, we don't have.
No, we don't have. We don't have explicit such conjecture. No. That's an interesting question, and Yes.